Okay, so we had talked about forming the sigma bonding molecular orbital and the sigma star anti-bonding molecular orbital for the hydrogen molecule. And we talked about how the sigma bonding molecular orbital is a region of enhanced electron density between two nuclei. So these two dots are the two nuclei in each hydrogen atom. And I'm just going to draw a faint outline of kind of what used to be each individual hydrogen's 1s orbital. So kind of between each individual hydrogen, we have this region of enhanced electron density that is really what's forming the covalent bond. So this is the bonding molecular orbital. And it is very stabilizing. It's a very stabilizing thing to have that region of electron density between the two atoms. So this is going to lower the energy of the electrons compared with how they would be in the atoms all by themselves. And we kind of saw that in chapter 3 when we talked about the bottom of the potential well with the formation of the hydrogen-hydrogen bond in the H2 molecule. Now, the opposite is the case for the sigma star antibonding orbital. We had this destructive interference creating a node in between the nuclei. And here I'm gonna shade. I'm gonna use shading to indicate opposite phase. So we have these kind of two oppositely phased regions, but in between them we have a node or a nodal plane, which is a region of 0 electron density. So that is an antibonding interaction. And this antibonding interaction, we always denote with a star. So I'm going to call it sigma star. This antibonding sigma star molecular orbital is destabilizing. It is destabilizing to have that destructive interference, that node between the nuclei. So this is actually going to raise the energy compared with how the free atoms would be in their respective atomic orbitals. So we can represent that energy difference by drawing an orbital interaction diagram. So this is going to be the first of many orbital interaction diagrams that we draw in this chapter. But in an orbital interaction diagram, your y-axis is energy. And on each side, I'm going to put the atomic orbital that I start out with. So I'm going to put 1s orbitals on either side because in hydrogen, each hydrogen, hydrogen A and hydrogen B, is going to have a 1s orbital. Of course, each hydrogen also has one electron. So I'm going to represent those electrons with these little arrows, just like we did with the orbital diagrams in chapter 2. Now, I know that when I do a linear combination of these orbitals, I get a stable bonding molecular orbital that I am labeling sigma. This is going to be my sigma 1s bonding orbital. And this is what happens to make the bond between hydrogen A and hydrogen B. But equally and opposite, I am also forming a destabilized high energy sigma star antibonding orbital. So you can see how the bonding interaction is lower in energy than the free atomic orbitals, whereas the antibonding interaction is higher in energy than the atomic orbitals. If I want to quantify this energy advantage that I get from forming the bond, the delta E here is going to be negative 215 kilojoules per mole. So that means that it's very favorable for these two electrons to form a bond. Those two electrons really want to be lower in energy if they possibly can be. So nature tends to seek the lowest energy state, and that's why the hydrogen-hydrogen bond forms. The energy advantage that you gain out of this is going to be equal to that delta E times 2, right? So we have 215 kilojoules times 2 electrons. So that's going to give us negative 431 kilojoules per mole. So the formation of the H2 molecule is very favorable because it lowers the energy of the system. Okay, so this is something that we learned about before in the bonding chapter, but we're just contextualizing it with molecular orbital theory. So another concept that we can talk about is bond order. Once you have drawn your orbital interaction diagram, you can calculate bond order by counting up the number of bonding electrons and subtracting from it the number of antibonding electrons that are in that middle of the orbital interaction diagram. And then you divide that by 2. That gives you the bond order. The bond order is important because it kind of is an index of bond strength. It tells you approximately how strong a bond is. So the higher it is, the higher your bond order it is, the stronger the bond. The lower it is, the weaker the bond. So what is the bond order for the H2 molecule? What is the bond order for H2? Well, let's go back to our orbital interaction diagram. I can see that in the H2 molecule, I have 2 electrons in a bonding MO and no electrons in the antibonding MO. So that means that my bond order is going to be 2 minus 0 divided by 2. 2 divided by 2 is just 1. So the bond order for H2 is 1. What would the bond order be for the H2 plus cation? Well, there I would have lost an electron, right? So if I lose an electron, that's going to be just 1 electron in that bonding MO. Minus 0 divided by 2 gives me a bond order of 1/2. What about H2 minus? Well, in that case, I'm going to have an extra electron. So I would have 2 minus 1 divided by 2, which also gives me a bond order of 1/2. So bond orders of 1/2 means that I don't even have a full bond. So neither the H2 plus nor the H2 minus ions would be stable species. But the H2 molecule with a bond order of 1 is a very stable molecule.